Lifting a steel structure weighing 10,000 tons to a height of 200 meters is not architecture. It is extreme bridge engineering in the air. The final assembly creates a continuous platform with a mass and length equivalent to a nuclear aircraft carrier, suspended entirely above a dense metropolis. Conventional tower cranes cannot handle this sheer volume. Engineers deploy strand jacking. Lasers shoot continuous beams across the lifting zone to establish a flawless initial alignment axis. Once the grid is set, heavy-duty hydraulic cylinders grip thick bundles of high-tensile steel cables attached to the payload. Pressurized fluid forces the cylinders upward, pulling the massive cables. The system instantly locks the strands, the cylinders lower to reset, and the cycle repeats. Stroke by stroke, millimeter by millimeter, the deep metallic groan of hydraulics echoes through the site as the mechanical tension reaches its absolute limit. A monolithic segment weighing 1,400 tons finally severs its contact with the ground. 14 million kilograms of solid steel slowly ascend into the sky. At an elevation of 200 meters, the physical environment turns highly unstable. Mild ground-level breezes accelerate into vicious, high-altitude wind shears. These atmospheric currents strike the enormous flat surface area of the suspended segment, threatening to transform the aerodynamic load into a devastating pendulum. Torsional misalignment becomes a critical vulnerability. An error margin of just 3 millimeters during the final approach would permanently shatter the structural connection nodes. The vertical tension cables hum and vibrate aggressively under the relentless atmospheric pressure. A real-time GPS monitoring system locks the exact spatial coordinates while the multi-ton block violently sways in the high-altitude crosswinds. Elevating the 1,400-ton sections during the previous phase served merely as preparation for the principal structural anomaly, a 67-meter cantilever extending outward from the northern edge. This observation deck projects directly into open space from the sheer precipice of Tower 3, leaving a steel mass equivalent to the length of a commercial jumbo jet suspended over the void without a single supporting column. Simple physics dictates that this extreme eccentric load should violently twist the framework and drag the entire roof downward. To neutralize this catastrophic rotational force, engineers embedded a colossal lever mechanism deep within the vertical concrete core of the skyscraper. Heavy steel bridge girders extend backward into the structural body of Tower 3, permanently anchoring hundreds of tons of dense counterweights completely concealed from public view. The forces cancel out. It functions exactly like a massive seesaw, utilizing the hidden ballast to prevent the projecting deck from overturning under the aggressive pull of gravity. Compressing months of continuous hydraulic hoisting into a unified timeline, crews guided the final aerial segments into their exact spatial coordinates. The structure locks. Formalizing this complex steel connection secured the permanent stability of the longest publicly accessible cantilever deck in architectural history. Locking the 67-meter cantilever did not suspend the laws of physics. Under high-altitude wind pressure, the three towers bend. Millions of liters of water balance on a massive moving pendulum. A storm front hits. The structure shifts. This kinetic energy threatens to instantly spill the massive 150-meter pool. Engineers at the CPP Wind Laboratory subjected a scale model to extreme aerodynamic testing. The data revealed a critical vulnerability. A rigid steel framework clashes with the continuous micro-adjustments of a liquid surface. The horizontal plane requires absolute zero alignment. To fight the sway, crews installed over 500 hydraulic jacking points directly beneath the basin. The wind strikes. The sensors detect displacement. The network reacts instantly. It executes rapid elevation corrections to keep the water perfectly level. Wind is only half the problem. Long-term ground settlement also warps the concrete geometry. To suppress microscopic vibrations rippling through the frame, engineers integrated a specialized tuned mass damper. It weighs 5 tons. Deep inside the upper deck, it emits a hidden low-frequency hum. This heavy mass absorbs the kinetic energy of the building, turning violent structural sway into a gentle glide. An automated network of underground reservoirs cycles the fluid. High-capacity pumps regulate the circulation without breaking the surface tension. The infinity edge holds its line perfectly. Tourists swim near the sheer drop. Below them, hundreds of mechanical pistons silently fight the wind in the dark. The moving water structure hovers 200 meters high. The foundation takes the punishment. Colossal eccentric pressure strikes constantly. The ground remains completely unstable. How do you support falling skyscrapers on liquid mud? 3 massive towers lean inward. Physics takes over. Dead weight ignores vertical lines. Eccentric bending moments build rapidly. Self-destruction looms. Curved structures attack their own base. They try to crush themselves. The earth offers zero support. Pure liquid mud. Groundwater floods the deep excavation. Lateral pressures crush ordinary walls. Engineers deploy massive drilling machinery. Steel teeth bite. Giant board piles pierce the muck. Shafts plunge tens of meters. Columns span 1 to 2 meters, wider than a car. Solid bedrock accepts the load. Total structural transfer. Risk hits zero. To anchor this towering anomaly against the shifting earth, the ultimate defense relies entirely on an invisible underground shield formed by over 5,000 board piles. Even an underground shield of 5,000 piles offered no protection against the physics of the ascent. The construction instantly became a race against gravity. Engineers chose cast-in-place reinforced concrete for the entire floor system. Pumps push the heavy wet mix into molds. The material cures. Another level rises. But with a severe structural lean of 26 degrees, every cycle adds massive eccentric dead weight. The building actively tries to crush itself. Lateral offset forces multiply exponentially. To stop a catastrophic collapse, crews deploy temporary bracing and a post-tensioned cable system. Thick metal tendons thread directly through the hollow walls. Hydraulic jacks pull these strands to extreme limits. Tension forces hit hundreds of tons per cable. The stressed steel groans under the immense lateral pull of the leaning concrete. Gravity pushes outward. The cables pull inward. Pure physical warfare. Then the timeline shifts abruptly. Months of dangerous structural tension culminate at the 23rd floor. This elevation marks the ultimate survival point. Heavy lift cranes lower massive connecting beams between the two opposing tower wings. The geometry finally stabilizes. Engineers cut the temporary restraints. Thousands of tons of inclined load instantly transfer from the tension cables into the permanent steel linkage. As soon as the concrete frame locked into place on the 23rd floor, engineers faced a critical density crisis. The construction crews had to embed a highly complex operational machine directly into the foundation of the megastructure. This sprawling base covers 845,000 square meters of internal space, roughly equivalent to 150 football fields. Planners compressed mechanical ventilation ducts, high-voltage electrical grids, and intricate internal circulation networks into a heavily restricted subterranean layout. The primary routing connects directly to Singapore's underground rail network, while the design team maintained strict fire safety regulations and preserved the original architectural flow. At the base of these heavy structural grids sits the lotus-shaped museum. It features 10 asymmetrical steel pedals anchored to a central diagrid hub. The entire curving framework consists of exactly 5,600 prefabricated steel components, assembled like an intricate three-dimensional puzzle. Zero tolerance. The fabrication yards manufactured every unique segment to precise geometric specifications. A single millimeter of deviation would ruin the continuous radial load path. This absolute precision proved that the spatial logistics and assembly tolerances at ground level easily rivaled the extreme engineering challenges of the high-altitude rigging. To transform this chaotic density of pipes and mechanical voids into a seamless functional environment, the crews required relentless forward momentum. The massive development consumed a staggering budget of $5.5 billion to merge the diverse commercial and structural elements. Despite the severe global economic disruptions caused by the 2008 financial crisis, the contractors maintained their aggressive schedule. The engineering teams completed the enormous volume of complex spatial integration in a record 3 years. This $5.5 billion engineering machine was not built for mere aesthetics. It was Singapore's aggressive strategic weapon in the ruthless fight for global financial flows. By the late 2000s, heavyweights like Macau and Las Vegas were rapidly draining entertainment capital from Asia. Singapore needed an immediate economic counterstrike. The stakes were absolute. The government put $5 billion on the line to physically transform the economy of an entire nation. The chosen battleground was Marina Bay. Singapore anchored its new financial capital directly onto weak, artificially reclaimed land. Beneath the surface lay a volatile, wet mix of saturated marine clay and imported sand. Load-bearing capacity was non non-existent, yet the master plan demanded 3 asymmetric towers supporting a solid steel roof 340 meters long. That equals 3 heavy football fields suspended 55 stories above the water. To open the resort by 2010, engineers had to force extreme gravity into submission. Tens of thousands of tons of steel and concrete would press directly down into a muddy seabed. Independent structural experts analyzed these early blueprints. They delivered a harsh verdict. The project was an impossible illusion. The race with Macau did not end in 2010. Singapore demands more. To retain dominance, they expand. This introduces a dangerous gravitational anomaly. Tower 4 rises 55 stories. It rejects the original symmetry. The steel frame twists violently. It leans at 45 degrees. This creates an extreme eccentric core. The leaning frame acts like a massive steel lever. Mass pulls away. Load distribution becomes highly volatile. A 15,000-seat arena anchors the base. 0 columns interrupt this massive span. High above, a cantilever deck projects outward. Dead weight crushes. Physics strikes back. Early estimates predicted $3.3 billion. Costs explode. Taming the radical eccentric load of this single asymmetrical tower drives the final expansion bill to an unprecedented $8 billion. The ultimate $8 billion question remains unanswered. Will the underlying ground and the laws of physics withstand this radical new 45-degree bend? The entire colossal weight of this gravity-defying mega project rests upon a treacherous bed of soft marine clay hidden deep beneath the bay floor. Engineers have already pushed the structural limits of this unstable Earth to support 3 perfectly balanced vertical monoliths. Now, a 4th twisting tower threatens to shatter that carefully calibrated equilibrium. A massive structure leaning at such an extreme angle concentrates dangerous eccentric loads onto a foundation with absolutely no margin for error. The original symmetry disappears. This $8 billion expansion introduces an aggressive asymmetrical design that actively fights against gravity instead of simply aligning with it. The sheer rotational forces pulling on the new subterranean piles will test the absolute breaking point of modern geotechnical engineering. Will this twisting masterpiece successfully redefine the skyline, or will its massive eccentric weight fatally disrupt the near-perfect balance of the original 3 towers?